Hopefully we're going to finish it off now this time. We're back to where we were at the end of the last video. It's a new day now. It's 10:23 a.m. on November 3rd. So I'm going to finish up the circuit. So we kind of came in here and we did some of this assembly, putting the pieces here. And this is kind of the way I like to do these board designs is I'll work on a part of the schematic, a big chunk of it. Then I'll get it all sorted out on the board, and then I'll go back and add more pieces to the schematic, come back to the board. Sometimes you got to move things around or delete things or change things, but normally it works out pretty well like this. It's a pretty daunting task. If you build a whole circuit on the schematic and then you jump to the board, sometimes what'll happen is it's easy to get lost. It's easy to kind of stop realizing what it is you're working on as you're doing the board layout. So doing it piece by piece, knowing what section of the schematic you're working on as you're piecing these things together, it can help you avoid certain mistakes. So let's go back and finish up our circuit. So we're gonna eventually have to create this 3-volt signal. That's gonna be the indicator to say that our voltage has exceeded 3 volts. So we're gonna have to use a comparator. We have 4 op amps down here. And so this is the output here is the output for this is our this is the output that again reference to ground tells us the voltage across our battery. So let's build these comparator circuits now. So I had these op amps down here just to make sure that they were all associated with the same U2, 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 U2. But I think what we might want to do is move them around now. So how do we know is we can move this. So we're going to do some comparisons here. So we're going to do one comparison that's going to check to see if we're over 3 volts. So when we want it to go, we want our voltage to go, to turn this transistor on when it exceeds 3 volts, we want this to go high when the voltage exceeds 3 volts. So to do that, we're going to have this input to the positive terminal of the op amp. And we can just wire it now. And then so on this negative terminal, we need to have a resistor divider that is going to produce 3 volts approximately. So let's go back and do that process again. Okay, I guess we should do this. So I'm going to steal these resistors. So one thing to note, when I just did this, I took R6 and I shift clicked it, and it says R. So I took R5 and I shift clicked it, and it updated the value to R6, which is probably not what we want to do because there's already an R6 that exists. R6 already exists here. So there is a way, I can't. There's a way to steal the part and not have it play games with the name, but I can't remember what that is. So let's go back and grab a register. So to generate 3 volts, we have 5 volt source. Let's go back to our resistor table. I don't have a calculator. I left my cell phone at home. All right, let's do. So, you know, again, if we want to do sort of 100 ohms total, we're going to need 3/5 of our voltage divided across our bridge. So we could do like a 60K and a 40K or something like that. So how close do we get? So if we want to do a 60K and a 40K, We can get a 60.4K. Can we get a 40.3K? 40.2, that's pretty good. So if we do a 40.2 and a 60.4, it's going to give us about 100K of total resistance across the divider. Let's just verify that. So it's going to be 604 divided by, we have 6 divided by 604 plus 402. That's going to be 6 times 5. 3, oh yeah, that's good. That'll be good. So for our 3-volt comparison, we're going to use a 40.2 kilo ohm resistor and a 60. Now this output, we want this to be this signal. So we had this signal 3V sig. So one thing I can do is I can just shift click this label, shift click the part label, and drag it over. So you got to be careful with these part labels because the signal label has to be, the bottom left corner of it has to be touching the wire or touching the end of the pin. So we could have had it directly touching the end of the pin. I usually like to extend out a wire and have it be on the wire. I think it's a lot easier to avoid accidentally having a label off of a wire if you have it. You always have a connected wire, always have the label on there. It looks a little bit cleaner too. I think it looks better like this than to have it just sort of floating offset from the wire, from the pin end. Okay, so this should, as soon as this voltage exceeds 3 volts, this is going to say, oh, I need to increase the voltage in the negative terminal. It's going to turn that on. That's going to cause current flow. Okay, now we have to have the shut off. So to shut this off when we finish here, I'm going to play some games here. Oops. Yeah, so to shut this off, to shut the flow of current off, we can ground this. So we can have a MOSFET that grounds this terminal. So it'll drive this reference voltage to 0, and that should drive our current to 0. So okay, yeah, so let's do that. So we'll do a other comparison. This comparison was on 1, 2, 3, 4. We could use the same side of the op amp. So that would be this op amp here. So we'll do the other comparison here. Once again, I want, when this voltage exceeds 4.2 volts, I want to produce it here. Copy this whole thing. Okay, so now to make a, now we want to make 4.2 volts. Go back to our trusty resistor table. So again, let's try to keep about 100K of total resistance. 4.2 volts, that would be 84 kilo ohms-ish on the low side. If we're trying to keep 100 kilo ohm total resistance. Oh, 84.5, it's pretty bad. So, and on the other side, it should be about 16. Hopefully a little more than 16. 160, 162 would work. 162 and 845. Check it. 84.5 and 16.2, I said. Yeah, so that's going to be 100, sorry, 1,000, 100.7. Yeah, good enough. Could we get closer if we do 164? Try that. So 845 divided by, so with 164 it would be 1,000. Nope. Okay, so 16.2K and 84.5K. How did I know it needed to be 100 kilo ohm resistance? Didn't. Let me make sure I'm actually recording. Yep. Okay, so now this one is producing. So this one now will, this will turn on the transistor to increase the flow of current as soon as we hit 4.2 volts. This one will drive our current down. Or sorry, as soon as we hit 3 volts, it'll increase our current. This one will turn off our current, set it to 0 when we hit 4.2 volts. But again, as you saw in lab, that's not actually gonna work like that. It's gonna turn it off and then immediately turn it back on. It's gonna kind of wiggle around a little bit. It's gonna hold the voltage at 4.2. So we're gonna need another 38 is already there. Again, making sure we have our body diode in the right spot. So we'll call this 4v2 sig. Short that 4v2. Okay, now here's the thing. When you short this, this should drive to 0 and it should drive this to 0, which in order to drive this to 0, it should have to have 0 current flowing through here. But sometimes these op amps don't quite 0. So sometimes, as you saw, you have a little bit of offset current. So sometimes a little bit of extra current will flow. And it might be nice if we could give ourselves a way to cancel that offset out. So just in case we have a situation where we notice there's still a little bit, even when it's supposed to be turned off, there's still a little bit of current flowing. One thing we could do is we could add a very large resistor to this negative terminal. So we could essentially create a small little voltage divider here. And that will just make sure that this will fully turn off. And if we overshoot, what it's going to do is it's going to actually potentially cause current to discharge the battery. But that's not going to be persistent. It's never going to actually discharge the battery because we're still feeding back on the 4.2 volts. So So if we add just a little tiny bit of extra, or give ourselves the option to add a little tiny bit of voltage to that terminal there, it could allow us to cancel out some of this current. Another way to think about it is if we have a little bit of leakage current into the op amp, we're going to inject that, or a little bit of voltage offset, we're going to produce that by injecting current through a high resistor on this terminal. We're not necessarily going to do, I don't think I'm going to actually end up building this. So what I'm going to do is I'm just going to steal a resistor from here. What I'm going to do is I'm going to give myself the option to do this. So I'm going to call this 1 mega ohm, and then I'm going to like this, and this is not a good design. This is getting a little ugly. So what I'm going to do is I am going to specify that this should not actually be placed. So I'm going to put on the schematic, and sometimes people do this with the part number, but I kind of want to have it be clear that we intend for this to be a massive resistance. All we're trying to do is produce a little tiny voltage to cancel out whatever offset we might notice in the op amp. And again, this is probably not something anybody's doing. This is just an in case. And so we'll have a directive. No. We'll just do say so DNP. So the DNP is basically telling the person who's doing this design, do not place this resistor. So if you had this schematic and you had the board and you were looking at the board and you'd see the number of resistors and you were looking, okay, what resistor value has to be there. If you see this, you would say, this is telling you do not place this resistor. And this is very common when in doing designs. Quite often, if you crack open, any motherboard to a computer, any circuit board, or you open up a cell phone, you're going to see all over that circuit board a bunch of resistor and capacitor locations that have nothing in them. It's just two little balls of solder, exposed pads, nothing connected. Very common in designs to do this, to give yourself the option to add a component later. If you don't populate this, who cares, right? If we don't put this resistor in here, it's just an open circuit, disconnect, it doesn't really matter. But by putting this resistor here, it gives us the option later to do this. Another place that people, if somebody were doing this design, they might want to put a resistor is in parallel with any of these dividers. So you might want to put an extra do not place resistor in parallel with here, in parallel with here, in parallel with here. And that'll give you the option to come back later. If you need to finally, precisely tune this resistance, it'll let you put two resistors in parallel, which gives you a lot more control over getting the exact resistance that you need. A lot of times it'll be you'll put a resistor on the bottom side of the divider that's a little bit too big, and you'll measure the voltage, and from that you'll calculate what extra resistor you have to add in parallel to get the exact value you're looking for. So that's a good practice if you need precision, but in general, this idea of leaving do not populate resistors just in case is very common. It's so common that, again, even the final version of these designs that end up in your hands as a consumer buying a consumer electronics product, almost always, they will have these parts that the designer had left the option to do something with, but they ended up not doing it. So do not place parts, very common. It gives you an option at least. And that kind of could be done with this, right? Let's say this was a consumer electronic product that we wanted it to either be able to charge one or the other, but they wouldn't do both. Then for one design, we would say do not populate one of these. For the other design, we'd say do not populate the other. And then the pad would be there, the footprint would be there. The actual one that gets populated would just be one, and the directive would be here on the schematic to tell the person. So. Okay, so this all looks good. Why don't we, for now, just go back to the design. Let's update it. Oh. Output pin, high impedance, output pin, high, yeah. So it's just doing an output to high impedance injection. So I don't see any major errors here. you want to look as it's doing this. Sometimes it'll have red check. If it fails, like it's usually if you use a part in a library that you don't have access to. Like let's say you design with a part from the R drive, and then your computer disconnects from the R drive. A lot of times you would see that show up here. You'd see a black or sorry a red X. So you do want to be checking as it's doing this process to make sure it's actually able to add all these parts and signals correctly. We have our op amp here, and the other thing to note is now all of these that we added have big text. They all have their big annotation. So sometimes when it first does it, I just go immediately find some more objects. Yeah, I go back in the schematic and say, okay, what's what? After I did the annotation. Okay, first thing, I want to build this. R14 and R15 make a divider. R14, R15. So unfortunately, the output of this op amp is going to be here, right? Yeah, maybe we actually want to move this op amp. This 14. And then this is 5. Anytime I change the grid, if I want to make the grid coarser to place parts, which when you're wiring, sometimes you do a fine grid. When you're placing parts, you generally want to do it coarse so everything is nice and aligned. And a lot of times, if you are on a fine grid and you switch it back to a coarse grid, you want to at least touch the part, right? At least move it a little bit so it snaps onto the new grid so you don't accidentally have things misaligned. So that looks like that's going to be pretty easy to populate like that. Let's do so. Also had R16 and R17. Another divider. Oh, I did it on the wrong one. Why did I do 8, 9, 10? Yeah, it was 5, 6, 7. All right, so I did this on the wrong. Connected this to the wrong op amp. So let's switch op amps here. So what I'm going to do is I'm going to move this off like that, and then I'm going to do design update PCB document. Okay. And then I'm going to go back and I'm going to put in this op amp. Okay, why did I do it in that order? Why did I remove the op amp, update, put the new op amp in? Because sometimes in Altium, if you take an op amp out and put a new op amp in, it really confuses Altium. Altium is like, okay, you had these signals connected here, and now a different signal is connected to it. Sometimes Altium, it'll get confused, and it'll say, I don't know what nets, you just did a swaparoo with 2 nets at the same time. I don't know what happened. I don't know what you want me to do. Do you want me to try to guess what you were trying to do? And usually it does a good job of guessing. But if you want to take the guesswork out of it, just do this. Just break the connection, update, put the new connection in, update. And that's a good way to do it. So, okay, so let's look at this. We got we got a 5V0 here anyway. Okay, good. Easier out. So this R13 is the DNP part. So this is to give us that option. Not good. Yeah, okay. So this is the DNP part. It was optional. If we want to squeeze that in there, it's a bad order of operations for me. So I'm gonna squeeze it in there. So I'm gonna do a little unrouting. So one thing you can do is if you want to select connected copper, you can do this and it'll select a whole thing of connected copper. And if you hit delete now, it shouldn't delete the pads. It'll just delete the copper connection. So I like this the connected copper. You can also like delete a whole signal if you want to, but in terms of removing stuff, sometimes that's a good way to do it. So I'm gonna sneak this resistor in between these two. Oh. Ooh, my labels were wrong. Ooh, that could have been bad. That could have been bad. Make sure you got the right labels when you do this stuff, I guess. Ooh, bad move, John. When you saw that when I was doing the other thing. Okay. Three spaces. Okay, so this. So we can reroute now. The Altium cut that stub there too when I did that. You know what? I know this 3-volt sig. I'm gonna have to get out here eventually. So I'm gonna. You don't have to get too much space. Trimmed it in an unintended way. Grounds, I'm still not too worried about the ground. We'll reconnect the ground later. This 3V sig, it does have to be routed. If I route it, I'm going to cut stuff that I want. Okay. Do something else. I gotta get this net R5 1 signal out of here. I'm trying to massage this so I can easily get. This will work. You're probably, as you're watching me do this, you're probably screaming at your computer screen. You see a better way to do it. I was never good at Tetris as a kid. I had a friend. It's Corey. He was really good at Tetris. Okay. Now we have net R5 1 available. .2B sig. That one I might also route a slightly different way. But I'm going to keep this Q2 close to the other stuff up here if I can. Because it's shutting down this divider. Remember that before I started playing games with it. We want this thing to be actually be able to pull it low. We don't want a lot of resistance on this path. Okay, well, you know, you can't always get what you want. Sometimes you gotta just start ripping. Not that much. Do over. Now advice, when you mess with the grid, readjust it. I already committed these signals I'm gonna have to pass. So signals that are gates of these transistors, because they don't have to be high speed. They, you know, we can have it be a long route and it should still be fine. But both these signals are gonna get popped through. It's fine. Should be fine. It'll be fine. Okay. Once again, reroute. Once again, I'm not worried about may plus this 5 volts. Okay, so the signals are gonna have to be plucked out. That'll be fine. Getting a lot of air wires here. Okay. I'll do it after everything else. Okay. That's good enough. I call that. Let's take a look at 3D. Make sure this is not too crowded. 3D. Good. So we want to be asking ourselves, can I place this? Can I actually put this part down here? Do we have space? Can I get tweezers in there? Yeah, it looks pretty good. Silk screen too, check it. We have a little misalignment here, but yeah, looking good. Doing some way because I want to be able to get this 5 volt out here. I'm thinking I want to route this out. How about I turn it this way? I could have the whole previous negative way. And so now we have to have our indicators. So this 3V sig, if this is low, that means that we are, this is low. It means that we're under 3 volts. If 4.2 is high, that means we're over. In between. Okay, so I'm going to do an oscillator circuit just to show you how to do that. So I'm trying to think what lights I could do. Okay, I have 3V sig, just have an under voltage light. Do something else. Yeah, that's what I want to do. So we're going to use the 3-volt signal. So the idea is that when it's under 3 volts, we want to have something to indicate that it's under voltage. When it's over 3 volts, we want to have it be something that that gives you a solid indication that you're charging. So I'm going to use this 3-volt signal. The 3-volt signal goes high when we reach 3 volts. It's low when we're under 3 volts. So when it's low, we want this thing to be, in this case, I'm going to try to make the light flash when it's low. When it goes high, I want it to be solid. And then eventually I need to turn this thing off when we've reached 4.2 volts, but let's get to that later. So I'm trying to minimize the number of, I'm trying to not have to use another op-amp package. So this is an oscillator circuit that we can use. We talked about this in class. And so what's happening here is you have a, this is a Schmidt Trigger comparator. So it's something that it compares these two values at these two inputs. And when one exceeds the other, it causes a Schmidt Trigger event to happen. And I want to just briefly mention. So Schmidt Trigger action. So this is the same circuit that's there, just this. So this is now flipped upside down, but it's the same basic circuit we had before. The idea here is, look, we have some reference voltage, and we have a voltage divider created by it. So we have a voltage divider here, and that volt on the positive terminal, and that's connected to the output. So as soon as its input, let's say this input voltage is increasing. As soon as this voltage input is increasing and reaches some threshold, the output goes low, right? When this negative terminal gets higher than the positive terminal, the output goes low. And in this case, what happens is when this output goes low, it causes this resistor R3 to pull down the voltages on the positive terminal. So we were trying to get all the way up to this V2, and then as soon as we do get up to that V2 once, boom, V2 changes. It drops down a little bit. It gets pulled down by the output voltage changing. And so now we're not going to reach the threshold in the other direction until we come back down to this lower V2. And then as soon as this voltage gets below that V2, the op-amp rails high, and now this R3 becomes a pull-up resistor. So now R3 is connected to the high output voltage. It's increasing the voltage at this terminal. So now we go back to, once we've gotten down to this lower V2, now again, we have to get up to this higher one. So this is Schmidt Trigger. This is pretty cool. So for your project, you might want to use a Schmidt Trigger. If you want to avoid these kind of transients that happen around 4.2 or whatever, you can use this calculator. It's really neat. So you can just do 5 volts. So let's say you want the trigger voltage will be like 4.2. Hold until signal drops to 4.1. Oh, it doesn't, it calculates the other direction. Oh, that's weird. Nice if it works the other way. Anyway, but this can be used to calculate these resistor values, right? So if we want R3 to be pretty small, yeah, pretty small there. Oh yeah, we can just use a divider here that gets us close to 4.2. So what do we have in the other one? The other one we had, to get to 4.2, what do we have, like 84, so 16-ish. 84. Make this mega ohm. Yeah, so that's okay. So that could give us some. This is a way that we could calculate this. 4, 6. Look at that. Okay, now we have something that it'll get up to 4.2 volts, and then it has to drop back down to 4.8, 4.187. So, but this is the idea of a Schmidt trigger. The one we showed in class. Is here. And this one uses the Schmidt trigger to basically, when it triggers in one direction, it starts charging a capacitor, which causes the trigger to go the other direction, and then it starts discharging a capacitor, which causes the trigger to go the other direction. So this one's generating this triangle wave as it charges and discharges the capacitor. This one's generating a square wave. But the comparison here, this middle of the road voltage is made by a voltage divider here. And what if we use as this ground, we use that signal that says we've reached 3 volts? If we haven't yet reached 3 volts yet, this is going to be low. If we haven't yet reached 3 volts, this is going to be low, and this is going to operate normally. It's going to make a blinky, flashing signal here. But when we reach 3 volts, this is going to go to 5 volts. So this voltage here is going to go to 5 volts, which means this voltage output will always be low. So this will hold low once we reached 5 volts. And then we can use this to our advantage. So for instance, if we use this then to drive the low side of an LED, easy. You can just drive the low side of an LED with this, and this will blink until it's done. Or we could drive a PMOS transistor on the high side of an LED, and again, that would also work just fine. So let's build this circuit using what we got. So we're gonna do, yeah, we got our op amps. We got 10, 9, 12, 13, so we'd be wrapping around in this direction, yeah. Oh, we gotta place a bunch of resistors. Let's do it right here, so we can just use 3V sig. Again, a lot of students think this is a feedback resistor because it kind of looks like one, but no, this is going to a positive terminal, positive feedback. So, I mean, that's what causes this instability, right? We have this circuit with positive feedback, causes it to latch one way and then latch the other way. We ultimately get negative feedback because of all of this that's happening. But initially, this short-term feedback is positive feedback. Positive feedback, and then slowly we get enough negative feedback to compensate for it, and then positive feedback, and then slowly we get enough negative feedback to compensate. So that's another way of thinking about it from a feedback perspective with that. there are here. We'll make it look like what we got. We don't make mistakes. Then we need a capacitor. Okay. So probably just to make the math easy, I'll just use a 1 microfarad capacitor. They're pretty easy to get. I'm gonna do cap semi. You got to be really careful here though. So cap semi, we want this one. 1608 metric 0603 imperial. Alternatively, we could go to the manufacturer part search. But you want to be really careful to double check the footprint if you're going to do something like this. So check the case code, check the metric. We want 0603. Oh, sorry, the imperial, we want 0603. So there's no 402, that's too tiny. 0805, that's too big. So we could use this. 1 microfarad 0603 X. Okay. So this should work. Let's check the footprint, see if there's multiple footprint. Oh yeah, we got left back. We generally want the biggest one we can get. Okay. Place. Make sure I didn't place 12 of them. Oh, let's save. Current license. What? License them without the swear. Now let us do it. Yeah. Okay, so we have a 1 microfarad capacitor here, RC time constant. So a mega ohm would be, about a second time constant. It's 1/2 RC, but yeah, because half the period, right? So 2 seconds. So if we want to make it flash kind of fast, we want this to be maybe 100K or so. And then we'll just do what they got in the rest of this. 47K, 100K. And then this is just creating a divider. So really could be mid voltage here. And in this case, you know, if we find it doesn't work, if we prototype it doesn't work, it's just a matter of changing the values. The design should still work. Triple check our work. It's really important to make sure you get these values right, because after you build this thing, unlikely you're going to come back and look at it again. So after you build it, you're just going to assume these values are all right. So if your value's wrong, you want to check it now. Okay, this is good. Okay. So then this signal right here is going to be our switch. This is going to be our switching on and off that is going to drive ultimately the LED. And it looks like it's going to be tough. I did the spaghetti wire of stuff, so I'm going to just label this right now. I'm going to give this a net label. Put it here. Okay, so now this is going to go. So after it is done, it's going to flash high, low when it's under 3 volts. Once it hits 3 volts, this is going to go up to 5. So this is always going to be low. So it's going to be solid low. So keep that in mind. Okay. Okay, let's do our indicator LEDs. So I'm going to do so for the flashing LED, I'm going to power it by a PMOS transistor. PMOS transistor. PMOS BSS 84C. Current be too bright. You can just do be precise about it. So say about 3 volts it's gonna have, let's do 1 milliamp. So close to 3K, 301. I think and one will be I like to just grab the net labels because I make sure I don't type it wrong several times. Okay. And then what do we want to do? We want when we reach 4.2 volts, we want to turn this one off. But 3.2 volts goes high when it goes high. So there's a cheap way we could do it. Goes high. Yeah, let's put another transistor in there. Transistors in series are like AND gates. No blocking with the body down, yeah. I'm playing fast and loose right now with this design. Definitely gonna want to breadboard this sucker before. And probably should have labeled it too, but I'm trying to be quick here. Okay. So what's happening here? So when we haven't hit 4.2 volts, this is going to be low. This transistor is turned on, no problem. When this one is flashing, it's going high-low, so that's turning this on and off. When this one goes over 3 volts, it's fully low, so both of these are on. And then as soon as it reaches 4.2, this one turns off. So it should fully turn this LED off. That looks good. I'm going to assume everything is right and just go from there. So my next one is I want to turn this on when we reach 4.2. So if I want to turn this on when we reach 4.2, then probably what I will do is label that VCC. Again, I should probably not be snaking this wire around, but I'm almost near the end, so I think it's going to work. I should have just labeled it, avoid these giant snaking wires, but all right, let's get the job done. Should. Okay, so now when this goes high, turns on this NMOS, turns on our green LED. So there's probably going to be a transition, right? There's going to be that little wiggle squiggle when this, as this thing is, starts pulsing or gets close to the threshold, it should kind of start turning these things off and on. So yeah, so might be a little squirrely behavior once again. We really probably, to do this right, should have added a couple extra op amps and done the latching behavior for the lights, but latching behavior for lights is probably better. I wanted to do it this way though. So, I think we're done. Are we done? We're done. Fine. Wow. Yeah, so that's all it's doing is the high V stuff. Got parts on here and I kind of threw in places. So, okay, so once again, to populate this, I'm going to go back to the schematic and see. We had so the top, or sorry, this is the bottom right op amp on that chip. So we got 200, so R18, R21 divider. I don't like that this cross is there. I don't like this cross there. And this, I mean, this happens, so this is pretty common, especially with me. You have to just constantly. Just good. Right, because that signal goes to both. I feel like we're gonna have to have a lot of circuit. Okay, but R22 is the bridge between. Okay, let's start putting stuff where it looks good. So first of all, this signal in the divider. We're gonna have to have a bunch of signals go to those transistors, and yeah, I'm pretty sure there'd be no good way without going through a bunch of stuff. You can also do is Altium's pretty smart. And if you drag like this, it'll stuff like that. It does intelligently route. It does intelligently move things. I don't want. Oh, I'm trying really hard not to do crazy stuff, but be concise. Distinct impression that switching these would help a lot. Get rid of your friend. Yeah, that's gonna help a lot. Normally, normally want to make big loops, especially with stuff going, but this is not an AC circuit, so there's slightly different rules for this thing. If it was a frequency issue with this, we might not want to play some of these games, but I think that's fine. Okay. 5 volts, ground. Nice. Nice, okay. Now we gotta get our LEDs and our pads. I gotta stop and go to a meeting, so until next time.